Good evening, everyone. Today we're going to present our project on building an end-to-end job data analysis, recommendation, and resume customization system. Here are the team members and their responsibilities. The goal of this project is to create an automated system that helps job seekers and analysts by using advanced AI and visualization tools. It will provide personalized job recommendations, generate tailored resumes and cover letters based on particular job, and offer insights into job market trends. Users can interact through a simple platform to upload resumes, access insights, and download customized documents. Finally, interactive dashboards will be used to visualize key trends and data for informed decision-making. This diagram shows how our system works to streamline the job search process and provide both personalized support for users and valuable insights about the job markets. We start by collecting, we use Airflow to orchestrate the entire workflow, including the scraper to collect job postings, step functions for dynamic job validation, loading data into Snowflake staging tables, and interactions with the vector database for intelligence queries. Start on the left, our scraper collect job postings from LinkedIn, storing the job data in the S3 data lake and maintaining job IDs for tracking valid jobs. The middle section highlights a step function which dynamically validates jobs using multiple Lambda functions, ensuring only up-to-date job information is retrieved. The data then flows into two key areas. The first one is Snowflake and analytics. So jobs are loaded into Snowflake staging tables, also registered in the Glue catalog for better metadata management, and processed with dbt, transformed with dbt, and finally Power BI to create a report and visualizations. The second one is a RAG workflow. So job embeddings are stored in Pinecone, a vector database, which interacts with OpenAI to power intelligent user queries. These queries generate personalized responses delivered through Streamlit. So on the right, users interact with the system to receive tailored job insights and recommendations. At the bottom, users interact with the system to receive modern infrastructure practices like Terraform and CI/CD pipelines are used to deploy and manage everything on AWS efficiently. Finally, security is integrated throughout the system using Secret Manager, IAM, KMS, and CloudWatch for robust monitor and protection. Here are the contents of our presentation.
Thank you, Sam. Next page, please. And let me walk you through our LinkedIn job scraping solution. For technical implementation, we are using a Python-based unofficial linking API created by Tom Kirk, which makes this approach powerful is that it interacts directly with LinkedIn's internal Voyager endpoints, the same ones used by their web application without requiring official API access. The key advantage of our approach include 3 points. The first one is that the direct data extraction without browser automation, which makes it significantly faster and more reliable than Selenium-based solutions. The second one is the comprehensive job data collection, including search results, detailed job information, and even required skills. The third one is a structured data retrieval that maps directly to LinkedIn's internal data model. Then to handle rate limiting and ensure reliable data collection, we have implemented several optimizations. First one is that we use 3 separate linking accounts, each handling different aspects of the data collection. Account 1 handles the initial job search. Account 2 fetches detailed job information. Account 3 retrieves the skills data. Then we use cookies to authenticate to avoid logging challenges. The cookies will be updated manually every 3 months. Then we've implemented asynchronous processing using Python's essential package to parallelize these API calls. And finally, we've added some configurable delays from 2 to 4 seconds between the requests to respect linking rate limits. For the data quality issue, We built in several safeguards. First one is the duplication logic to handle cases where jobs appear multiple times during the pagination. Second one is the time window validation to ensure that we are not collecting duplicate data across different runs. The third one, fourth one are the error handling and validation before saving our data to the data lake, and a comprehensive logging system for monitoring and debugging. The scraper outputs data in error format, which provides efficient storage and strict schema validation, ensuring our downstream processes receive consistent, well-structured data. And this approach has been proved both reliable and scalable, allowing us to collect comprehensive job market data while maintaining good citizenship on LinkedIn platform. Next page, please. And this is our automated job validation pipeline that filters out expired LinkedIn job postings to keep the job info up to date. The workflow is orchestrated by step function, which consists of three main components: a starter lambda that orchestrates the workload distribution, then multiple worker lambdas that perform parallel validation checks, and a collector lambda that aggregates results. First, the starter divides the jobs into manageable batches based on the number of jobs. Then each worker lambda checks its assigned batch of job IDs to identify invalid postings. The invalidated postings could be expired, closed, or removed. Finally, the collector lambda combines all results, create an invalidated job list, and update the main job database by removing these invalidated entries. This distributed approach allows us to process large numbers of job posting while respecting rate limits. Next page, please. And then I will talk about the data lake, sinks, and storage. Firstly, let me walk you through our storage architecture and why we specifically chose error format. Our system uses a two-tier storage approach, Amazon S3 as our scalable data lake, feeding into Snowflake for data warehousing. The key differentiator in our architecture is our choice of error format. We chose error for four critical reasons. First, it provides strong support for field evolution. Error allows us to adapt our schema without disrupting existing data. And second one is error stores the schema with the data itself, ensuring data self-documentation and consistency. Third one is that it includes built-in schema validation, preventing data quality issues before they enter our pipeline. And finally, error uses efficient binary compression, reducing our storage costs. And this combination, S3's scalability, error's robust features, and Snowflake's powerful warehousing capabilities creates an efficient and maintainable data pipeline. And next page, please. And we use AWS Glue Catalog to serve as our metadata repository. We use Terraform to define our data catalog structure, including database, data table schema, and partition strategy. Our Glue table is partitioned by year, month, day, and keyword. The schema matches our error format, handling both primitive types and arrays. The Glue crawler keeps our metadata up to date, using a security configuration for S3 encryption and following a schema change policy that logs any modifications. And this is part of the Athena query result. And next page, please. Then for the data processing, and we use Lambda. Our Lambda functions extract jobs data from linking with Python. For each search keyword, it authenticates with linking APIs, executes searches, and collects detailed job information and skills, descriptions, and requirements. Finally, the scrap data stored in error format in S3. Also, the Lambda's 15-minute timeout is sufficient for our scraping task. With serverless execution, we get automatic scaling and cost efficiency, paying only for actual runtime. Then the orchestration part will be introduced by Sam.
So for orchestration, we use both Airflow and step functions. The pipeline is triggered daily to scrap jobs posted in the past 24 hours. Airflow provides flexibility, robust monitoring, and integration with a wide range of services, making it ideal for complex workflows. And step functions excels at orchestrating tasks within the AWS ecosystem. So during the job validation step, we need to dynamically split the workflow and a workload and invoke multiple Lambda functions to call the linking API from different IPs to avoid being blocked. So while Airflow is a powerful orchestration tool, it has some limitations in handling such dynamic workflows efficiently. Its static DAG structure makes it difficult to adjust workflows on the fly. And the Lambda invoke function operator is not deferrable, which means workers are either blocked for up to 15 minutes during synchronous invocations or left unable to track success or failure of asynchronous Lambda runs. By integrating with AWS step function, we address these challenges. Step functions provide native support for dynamic workflows, allowing the first Lambda to determine the number of subsequent Lambda functions required and orchestrating their execution seamlessly. And moreover, step function start execution operator in Airflow is deferrable, so it doesn't occupy workers while waiting for the step function to complete, greatly enhancing resource efficiency and scalability. The combination allows us to leverage the strength of both tools to achieve an efficient and scalable solution. Here is a demonstration of our workflow. Our workflow pipelines begins with the linking scrapper, as shown here, which extracts new job postings. The scrapper stores the job contents in an overall file and records the job IDs in a CSV file that maintains a list of all current valid jobs. The Lambda function is invoked asynchronously, so we cannot directly track its execution status. Instead, we monitor the creation of the overall file in S3. So if a new file appears, it confirms the scrapper job was successful. Next, the pipeline branches into 3 parallel streams, as shown here. The first stream adds the new job posting into the vector database. The second stream loads new job data into Snowflake staging table. So first we truncate table and load new data. And third stream invokes a step function to validate whether the job IDs in the CSV file are still valid as of today. So we can have a quick look. So this is most current run today, and we can see 5 different lambdas, 5 same lambdas are invoked, and they work in parallel. After validation, any jobs deemed invalid are removed from the vector database. Additionally, both invalid and current valid job IDs are loaded to the Snowflake staging table. And finally, the pipeline collects the results and sends a notification email summarize the run, as shown here. The task IDs and their corresponding output. We can see we run it today, and 164 new jobs are scrapped, and totally there are 663 jobs that are valid in the market. And today we found 9 jobs that are invalid and thus removed. So this setup ensures efficient processing, validation, and tracking of job posting through Airflow. Okay, so security aspect. Our security setup for MWAA ensures both strong authentication and robust authorization. Users authenticate to MWAA using AWS credentials with optional multi-factor authentication for added security. Permissions and roles within Airflow are tightly managed through AWS IAM policies, while the MWAA execution role defines what actions Airflow can perform on AWS resources. Within Airflow, we configure the Fernet key to enable encryption of variables, connections, and XCOMs. We've also integrated Secret Manager, AWS Secret Manager as a secret backend, which securely stores and manages credentials like API keys and connection details. So this allows Airflow to securely access third-party services, including Gmail for email notifications, OpenAI and Pinecone for managing vector databases, and Snowflake for handling data extraction and loading into the warehouse. Okay, I will hand over to Kevin, who will introduce our RAG.
Thank you, Sam. So I'll just take over the screen share for now. One sec.哎，我需要那个重启一下，因为它这个好像需要给一下权限。很快，稍等。
OK。哎，要么咱先说下面的吧。
对，你们要不先开始下面的部分？
行，那个 Jasper 准备好了吗？
能听到我吗
？OK，我 share 一下屏幕，稍等啊。
？OK，好。SM，你还要再 share 吗？
对啊，因为那个 Kevin 他不在重启吗？
哦，好，
待会儿他来了再说呗，好吧？这个是 Kevin 的。OK。
Hello, my name is Jasper, and for me is the data transformation and reporting part. And next page, please. And this is my flow chart of ELT pipeline. First, we will import data from S3 to import raw data to Snowflake and use dbt to do the transformation job. And after we get enriched data, we can use our data to analyze using the Power BI. And next page, please. And this is the detailed data transformation using dbt. And first, after we import the raw data from the S3, we separate them into staging layer. In this layer, we do some basic data cleaning and standardization. And next step, we more separate them into different dimension layers. And more specifically, we use bridge layer to handle many-to-many relationships. And finally, we get final facts tables. And I also add 3 fact tables for specific jobs on skill change, location analysis, and post quality. And next page, please. And so to sum up, we use a star schema, and we have 2 aspects of fact tables, the main fact tables and analytical fact tables, and dimension design is as shown on the picture above. And next page, please. And for the visualization part, we use Power BI for this part. And because Power BI compared to other tools and have a lot of advantages, so we finally choose this as our tool to analyze our data. And next page, please. And this is our first page of our Power BI analyst. And we can see that on the top left, most of our data engineer job is located in Sydney and Melbourne, and small part in Perth and Brisbane. And we can see on the bottom left, and is the most company that release data engineering relative job. We can see that People Bank, Commonwealth Bank, AWS, they post most. And we can see on the right bar charts, this is the skills that top needed for our data engineering. And we can see that AWS, Python, ETL, Spark, SQL, all is most demanding skills in it. And next page, please. And we also analyze the workplace type and sanitary level. And hybrid on-site is the most workplace type for us. And of course, mid-level, mid-senior level, and entry level are the most sanitary level that our job needs. And that's all. And let me hand it to Rowan for the next part.
Next page, please. Thank you, Jasper and Sam. And I will introduce our DevOps part. For our DevOps approach, we've selected key tools to streamline automation and monitoring. First, Terraform to automate the infrastructure setup. GitHub is used to version control and deployment workflows. And Airflow is used to orchestrate. CloudWatch is used to monitor and to monitor the system performance and logs. And these tools work together to enhance our collaborations and efficiency. And next page, please. And for the infrastructure as code part, the reason why we choose Terraform for our automation is because Terraform solves 3 key challenges. It enables infrastructure as code, provides multi-cloud support, and ensures consistent environments across our development lifecycle. Terraform's multi-cloud capability sets it apart from CloudFormation's AWS-only limitation. Its developer-friendly HCL syntax offers better readability than JSON or YAML, simplifying the coding and maintenance. State management provides precise infrastructure change control and enabling fast deployments and better dependency handling. And the right side is an example of our file structure, and let me explain it. Everything starts with the main.tf. It is where we define our infrastructure components. To make our code reusable, we use variables.tf to declare parameters that might change between environments. The actual values for these variables are stored in the Terraform.tf vars. This structure can reduce our deployment errors and improve our team's collaboration through version control infrastructure. And next page, please. And then we use GitHub Action for CI/CD. And in this slide, and this is an example workflow for the Lambda function deployment. Our Lambda function deployment pipeline implements a change detection system using SHA-256 hashing. Before deploying any function, the system compares the hash of new zip file with the existing hash stored in S3 metadata. This ensures we only deploy when there are actual changes, preventing unnecessary deployments and maintaining version control. Each deployment is tagged with a timestamp, allowing us to track versions and identify expired functions. The system integrates with Terraform for infrastructure management and automatically handles both new deployments and updates to existing functions. Terraform plans for each deployment job are stored in S3 bucket for management. We also used GitHub Actions to deploy and update IAM roles, group catalog, step function, and other AWS resources. Next page, please. And we use GitHub for code repos and CI/CD. We organize our project into multiple GitHub repositories, each is dedicated to a specific part of the system. For example, we have separate repositories for the scraper, orchestration with Airflow, DBT for data transformations, and the rack workflow. This approach helps us to keep the code modular, maintainable, and easier to collaborate across different components of the project. We also use Jira to plan and track tasks effectively. And then we'll hand to Kevin for the rack part.
Yeah, thank you. I'll try to share my screen now. It should work. Bear with me. Yeah, works. Oh, sorry. Okay, thank you. So today I'm here to share how we are leveraging modern AI technologies, specifically retrieval augmented generation or RAG, to revolutionize the job hunting process for applicants. So let me walk you through the system architecture and then demonstrate in action. So at its core, our system solves a critical challenge in job searching, which is how do we effectively match candidates with the right opportunities while providing personalized guidance? Well, our solution combines the power of semantic search with Gen AI to create a more intelligent job matching system. Looking at our architecture diagram, so we start with two key inputs. One is the candidate's resume, and another one is the job database. So this document goes through specialized parsers that extract and structure the relevant information. This structured data then flows into our embedding pipeline. The embedding stage is where we transform the parsed text into rich numerical representations that capture the semantic meaning of both resumes and job ad. These embeddings are stored in a vector database, enable efficient similarity searches. In the matching phase, we use semantic search to identify the most promising job matches for a candidate given their resume. But we don't stop at simple matching. This is where RAG comes into play. We feed these matched pairs along with the original documents into our Gen AI agent. Using carefully crafted prompt templates, the agent generates three types of valuable outputs. The first one is the detailed match analysis explaining why certain jobs are good fits compared to other jobs. Second, a personalized resume feedback to help candidates better position themselves. And third, you can ask for a tailored cover letter suggestion that highlights relevant experience. Now I will do a short demo. So we are using Streamlit for the front end. So first, I need to upload the resume and the position I want. You can add any filters if you like, but I'm just going to start analyze. It will take a few seconds, so. Yeah, so here we get all the suggestion and the matching jobs here. So we can ask for a cover letter. I will just ask it to write me a cover letter for the top matching job. Basically, what it's doing is just talking with OpenAI as a backend, and just, yeah. So here we can get a, I guess, a tailored cover letter just for that job, and you can just modify however you want. Yeah, and I think that wraps up with our presentation. Thank you very much.